The next contribution will be with heteropoly acid as catalyst for Werkhoff phase hydrogenation of carboxylic acid. So this is a joint contribution from the University of Liverpool and Ashford, UK, and the lecture will be given by Dr. Kovnezokov.
Thank you very much, Mr. Kara. Good afternoon, ladies and gentlemen. It's a pleasure and honor for me to speak here on the respect centenary conference, and I would like to thank the organizing committee for the opportunity to do so. I'm going to talk about hydrogenation of carboxylic acid to aldehydes. Aldehydes are used as flavors and fragrances as well as intermediates in production of dyes, other chemicals, and pharmaceuticals. Most aldehyde syntheses, however, are non-catalytic, producing large amounts of waste. Hydrogenation of carboxylic acids by heterogeneous catalysis and vapor phase is a leading route to aldehydes using inexpensive and readily available carboxylic acids as feedstocks. Metal oxides are often used as the catalyst, and chromium oxide is employed for manufacturing aphalic and aromatic aldehydes by Mitsubishi in Japan. Now, why heteropoly compounds? These compounds have found extensive usage in catalysis, mainly acid and oxidation catalysis, as demonstrated by Professor Misona in his plenary lecture this morning. Heteropoly compounds comprise nanosized metal oxygen cluster anions, also called heteropoly anions, and often considered molecular oxides due to their discrete structure and chemical analogy to the constituent metal oxides. These compounds exhibit unique properties, with multifunctionality and structural mobility being the most important. There are many structural types of heteropoly compounds, but one type, the Kagan compounds, with such heteropoly anions, are most frequently used as catalysts. And to our knowledge, little research in catalysis by heteropoly compounds for hydrogenation has been done so far, and those are useful reference, general reference to catalysis by heteropoly compounds. And here you can see the well-known structure of the Kagan heteropoly anion in different representations, as well as some typical examples. In this work, we used Kagan molybdenum phosphates. The Kagan molybdenum phosphates, in particular, these heteropoly acids and their cissin salts are important oxidation catalysts. For example, for industrial oxidation of methachlorine to methacrylic acid by oxygen. In this work, our objectives were as follows. First, to investigate catalysis by these heteropoly compounds for the vapor phase hydrogenation of propanoic acid to propanol. And secondly, to examine the relation between hydrogenation and oxidation catalysis by heteropoly compounds. Here you can see our catalyst and research conditions. We studied three groups of catalysts, all bulk Kagan heteropoly compounds, based on molybdophosphoric acid and its mono and diaminating substituted derivatives. The Kagan, the cissin content varied from 0 to neutral sign, to neutral salts, to control catalyst acidity. And this catalyst surface area varied with the composition within those ranges. And the last column shows catalyst thermal stability, which is the temperature of decomposition to oxides measured by differential scanning calorimetry. I just want to mention that the monovanadium compounds are the most stable in this series. The reaction was studied using fixed bed microreactor, 350 degrees C, 1 bar pressure, 2% propanoic acid in hydrogen flow. It's important to mention that the catalysts required thermal pretreatment to improve their activity. It was done in situ, 400 degrees C, and hydrogen, typically for 2 hours. Increasing the pretreatment time improved further the yield of propanol. Here you can see catalyst performance, and this is monovanadium catalyst. The conversion of propanoic acid and the selectivity to propanol. You can see here that the parent heteropoly acid shows high initial activity but quickly deactivates due to corrosion. Cesium salt exhibit more stable activities, and their activity decreases with the cesium content. Other catalysts based on molecular phosphates and diamine show very similar performances. And this shows the steady-state performance of the monovanadium catalyst. And the chemistry involved is schematically represented here. The desired reaction, this one, top, this is the hydrogenation of propanoic acid to propanol. And there are two main undesired reactions. First, the hydrogenation to yield propane, occurring probably via 1 propanol. And the other one is the formation of ketone, 3-pentanol. And this reaction does not require hydrogen and occurs probably via cesium propanoic acid intermediate. What is important here that the catalyst acidity plays a key role and greatly affects both catalyst activity and selectivity. And the catalyst acidity is varied by cesium substitution from the free heteropoly acid to the neutral cesium salt. So you can see that the activity passes, activity that's conversion represented by sodium bars, passes flat maximum. The parent heteropoly acid shows very high activity, that's formation of hydrocarbon, propane, with no ketone formed. Open bars represent the selectivity to desired propanol. And you can see that the selectivity to propanol passes maximum 76%. At the same time, the selectivity to propane decreases monotonously in this series, whereas the selectivity to this ketone increases in this series. And this is a summary of steady-state catalyst performance after 12 hours downstream. Test results for aldehyde formation are shown in bold red. And what you can see here, all three groups of catalysts show quite similar performance, 71 to 76% selectivity, propanol selectivity, and 40 to 50% propanoic acid conversion. However, the more stable monovanadium acid shows a slightly better yield of propanol. We characterized our catalyst both fresh and spent, and here you can see our X-ray diffraction data. All fresh catalysts are crystalline substances. However, after reaction, they all lose crystallinity. And actually, the crystallinity is lost already after catalyst pretreatment. And this graph shows in situ XRD data for monovanadium catalysts, which show catalyst evolution during pretreatment at 400 degrees C under hydrogen. So, crystalline at room temperature, catalyst gradually becomes amorphous on heating at 400 degrees C under hydrogen. This is the surface area of monovanadium catalyst before and after reaction. And you can see that after reaction, the surface area is significantly reduced. And this shows the FTIR spectra for all catalyst types, fresh and spent. So if you take a look at this one in the middle, this is the most stable monovanadium catalyst. So from this spectrum, it is clearly seen that the catalyst retained the primary structure, Professor Nisson, after reaction. So this is fresh, this is spent. But it is different for the other two. So the less stable molecular phosphates and divanadium derivatives undergo decomposition. Fresh and spent, fresh and spent. From these data, we can conclude that the initial crystalline heteropolyl compounds are catalyst precursors rather than the true catalysts. We did some kinetic studies of propanoic acid hydrogenation over monovanadium catalysts. So we used differential conditions at conversions less than 10%, and propanol selectivity was 74–76% in such conditions. We found that the reaction is zero order in propanoic acid in temperature range study. Right, so that's between 320 to 380. The reaction obeys the Arrhenius equation with motivation energy of 85 kilojoules per mole. And the reaction rate does not depend on the flow rate at constant contact time. These results suggest that the formation of propanol occurs in chemical regime without diffusion limitation. Now I would like to talk about reaction mechanism. There is a compelling evidence, mainly from Hereropoly and co-workers studies, that the hydrogenation of carboxylic acids to aldehydes over metal oxides proceeds via Marsland-Crevenden type redox mechanism. Here, this mechanism adopted for the formation, for the hydrogenation of propanoic acid is shown. And the mechanism involves two studies, two steps in which the lattice oxygen plays a key role. So in the first step, the lattice oxygen reacts with adsorbed hydrogen to generate oxygen vacancy by dissolving of water molecule. In the second step, this vacancy is refilled by oxygen from the substrate of propanoic acid to yield the aldehyde and regenerate the catalyst. From our data, the hydrogenation of propanoic acid over molybdenum phosphate heteropoly compounds fits well into this mechanism. And step A is probably rate limiting, since the reaction is zero order propanoic acid. The question is now whether the formation of such oxygen vacancies is feasible in the case of bulk heteropoly acid. The answer is yes. And actually, back in the 1980s, Professor Nisson and co-workers investigated the reduction of bulk heteropoly acids, for example, molybdenum phosphoric acid, with hydrogen, and showed that this reaction can occur with water evolution, leaving behind deficient polyamides with oxygen vacancies. We tested this using in situ TGA. So the results are shown here. We did observe weight loss on catalyst reduction by hydrogen at 340 degrees C, as demonstrated here. And the higher the cesium content, the more resistant Hereropoly compound is towards the reduction, which is in line with their activity in propanol acid hydrogenation. So these results support our suggestion about occurring the reaction via Mars-Van redox mechanism. Now I would like to comment on the relation between hydrogenation and partial oxidation of heteropoly compounds. Reduction and oxidation catalysis by heteropoly compounds shows certain common features arising from the molecular oxide nature and multifunctionality of heteropoly compounds. Catalysis by molecular vanadium phosphate heteropoly compounds in hydrogenation bears a close resemblance to that in heterogeneous partial oxidation by oxygen. For example, oxidation of methacrylate into methacrylic acid, which was studied in detail by Kovnezokov and well documented in the literature. First, both reactions occur via Mars-Van mechanism, which is typical of metal oxide redox catalysis. And secondly, the acidity of heteropoly compounds plays a fundamental role in both reactions. Both involve bifunctional acid redox catalysis. Interestingly, the resemblance can be further extended to homogeneous oxidation by dioxide. Many homogeneous oxidations catalyzed by molecular phosphoric heteropolymers, HPLN, occur by a redox mechanism involving oxidation of substrate by HPLN, followed by reoxidation of reduced form of HPLN by oxygen, which is actually similar to Mars-Van mechanism. The homogeneous oxidation also involves bifunctional acid redox catalysis, and precise control of acidity is crucial for the catalyst efficiency in homogeneous systems, as is well documented in the literature. Now we come to conclusions. So we found that the Kagan molecular vanadium phosphate heteropoly compounds are active catalysts for vapor phase hydrogenation of propanoic acid. Catalyst acidity has crucial effect on the catalyst activity and selectivity. The initial as-made crystalline heteropoly compounds are catalyst precursors rather than the true catalyst. The secondary structure of the catalyst changes during the reaction, so it's crystallinity and surface area, although the primary Kagan structure can remain intact if a catalyst thermal stability is high enough, like in the case of mononative system. The formation of propanol over heteropoly compounds is likely to occur by Mars-Van mechanism. And finally, catalysis by heteropoly compounds in hydrogenation bears close resemblance to that in partial oxidation by oxygen in heterogeneous and homogeneous systems, which probably arises from the molecular oxide nature and multifunctionality of heteropoly compounds. I would like to acknowledge the funding and financial support from Liverpool University through the German grant scheme, and also industrial support from Western International. Well, thank you very much for your attention.
Thank you, Professor Kovnezokov, for this very interesting lecture, which is now open for discussion. Yeah, go ahead.
As I understand, the limiting step on the surface reaction is oxidation of hydrogen, right?
Yes.
Yes. And from the other hand, from the TCD data, the most active catalyst was the slowest in oxidation of hydrogen, or it was not the most active catalyst. In your second slide for the TCD data with different heteropoly acids and reaction of reduction of oxidation. Well, they
The conclusion about rate limiting step is based on kinetic studies and zero order with respect to propanoic acid is indication of that. Well, regarding to sort of the activity of a particular heteropoly compounds, we have to consider exact conditions as well as bearing in mind whether it's initial activity or steady state. So the data that shown over there actually was steady state results after 12 hours time on stream. So you probably cannot directly correlate.
Any other question? So I have a short question. In one of the slides you have presented, I think it was on the molybdenum-vanadium system, when treated in the hydrogen, you mentioned that you lost the crystallinity
Yes.
of the sample. What happened if you reoxidize the system?
Well, we haven't done it in our work. It's difficult to comment. It could be both ways. It depends on the reoxidation conditions. I would speculate that sort of, if it's dry reoxidation, we will end up probably with amorphous material. If it's wet oxidation, most likely the crystallinity will be rebuilt.
Okay. No other question? So thanks again, Professor Kovnezokov, for this lecture, and thanks to all the speakers this afternoon.